Student at Western Kentucky, and this is my BDAN517 Capstone project. Okay, we are just going to jump straight into it. I only have 8 minutes, and every time I do a dry run, I'm about 13 minutes, so I'm going to try to do this as quick as I can. So we're supposed to predict the body fat percentage using this data here, body measurement. Body fat percentage is going to be a numerical value, so we're going to use a decision tree regression, and then we're going to do a nonlinear regression as well. Here is the R script for that. To build the data tree, we're going to need to make sure our part function is in our library. We need to do that by making a code for it, or we can go into the packages and make sure our part is selected. Here's a summary of our data. I've already gone through the data. There's nothing missing. All the values look to be usable. Nothing crazy that's going to skew anything. Nothing that is just wild. Okay, jumping straight into it. Building the model. So our model is going to be built on this one code here, that regress tree R part. Then our body fat is our dependent variable, so the variable we want to predict, and then that period here is going to signify that we're going to be using all other 15 variables to predict what the body fat percentage is going to be at the end. The data we're going to use is that data I just imported, that body measurements. So we'll click run on that. Then here's a plot to see what that model looked like. All right, making predictions. So we have the 252 observations, and here's what goes with every single observation. So the first one's 13.43, 5.54, 25.66, so on and so forth. Okay, evaluating the model. We're going to use the root mean squared error to see how far our predictions were off from the actual value. Here's a summary of all of that. Each node, each observation. We can go through and look at all those, but I don't know if we have that much time. Okay, now we're going to split the data, see if we can get our model even closer. Set seed 25. Set seed is just the 25th option of how to partial up that split data. So we're going to use 0.8. So 0.8 of the data will be going toward testing, and then the other 0.2 of the data will be going toward testing. I think I said 0.8 going towards testing. It's actually 0.8 going toward training the model, then 0.2 going toward testing that actual model. Okay, we'll run that, and we got our testing data there and our training data there. Regress tree, same thing, body data. And then we evaluate that, and with the split we got 0.4 units closer, so our model's getting a little bit better. And then we're going to use our nonlinear regression model. We don't need the read Excel. I imported the body measurement data there. And here's the structure of all that. We kind of already looked at that. Here's the different values that we're going to test on: the age, weight, height, density, thigh, hip, knee, ankle, bicep, so on and so forth. Okay, and then we're going to just manually split it. So we're going to say the first 200 observations are going to go toward training the data, and then the remaining 52 are going to go toward testing that data. Okay, we'll run those and run those. All right, you got test data there and then training data there. Not to get those confused with these two. Okay, creating that model, model 1 and model 2. In my brain, I was like, weight should have a big correlation of what your body fat percentage is going to do. So I gave weight double the weight to help predict our model. All right, so here's our predictions. Looks like they're pretty much both predicting the exact same thing. Then we get the root mean squared error for both of those to see how each model did against each other, and then you get that 0.86 away from the actual value, and both did pretty much exactly the same. The last two numbers, which is in like what, the hundredth, or sorry, the millionth decimal. So they did pretty much exactly the same. Very, very, very minute difference in those. Okay, we are going to clear out our environment windows and clear out our R script window. Actually, we'll go back to list, and then we'll just do them all at the same time, so we don't have to click through everything. Okay, great. Okay, we'll just upload that loan application data set real quick. Okay, perfect. And then my R script for that. Okay, great. This is going to be a classification model for this one. So I'm going to be using decision trees again, and then logistic regression for the second model. Okay, we can look at the structure of the loan application, or we just do the drop down there. It looks like everything's either character or numerical. That means we have some cleaning to do on it, since we are going to be predicting binary for the set. The model wants to look at numbers and not classification or characteristics. Sorry. So we're going to do a little bit of cleaning. So we're going to name our new data a data frame, and then we're going to clean up this. So married, going to be two factors, one being yes, two being no. Education, self-employed, property area, and loan result. Those are all characteristics. Now they're all factors. Got to look because some factors aren't two, some are three. Property area is either rural, urban, or semi-urban. And I ran into a little bit of trouble the first time I did it because I didn't know there was rural, urban, and semi-urban because I only saw the rural and urban, and it was giving me a whole bunch of trouble because there was some missing data because I only had those two factors in there. Okay, we can run the summary on that. Like I said, I only have 8 minutes, so I don't want to go too in depth, but it looks like we have no missing data in all 272 observations, so that's good. We'll just jump straight into making those models. Set seed 68, just arbitrary number. So we're going to split it into 70-30 this time. That's just to break up the 80-20. So we're going to partition that training data and that testing data. Creating the model is that one line. Our part, we see it again. This time the method is going to be class. Type is going to be class because it's a classification regression. All right, here is our predictions with no being 1, which is not approved, and yes being 2, which is approved. In testing that against the actual results, we get 81.4%, 81.5% of our values being correct. You get that true positive or false negative. Okay, we're going to be using that logistic regression model now. For that, we're going to have to use the caret function in the packages. I've had trouble getting that approved using the R script function, so I have to usually go in there and make sure characters clicked manually. All right, building that logistic regression model, you're going to use GLM, which is a generalized logistic model. Still predicting loan results. The period is to use the other 11 variables to help predict loan results. Okay, we build that model, and here's the summary of that model. Okay, in predictive class, we're going to set it at 0.5, so no being 0, yes being 1, and then we're that line at 0.5 is going to give us what our accuracy is. So if it's above 0.5, then it's a yes. If it's below 0.5, then it's a no. So here you see that predictive probabilities. So this would be a yes, 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 yes. Okay, when we run that, we get the accuracy of about 0.8493. 0.8493. Oh, sorry, we got it down here. Cat. Okay, accuracy is 0.8493 here. Here it is right there. Okay, sorry about that. All right, cross validation. So I want to just validate our model. We're going to do 5 folds in that one set seed of 100. We already did the my control. For cross validations is the CV, set seed 100, building that model again, training it, and now we're going to put in that verification. And this time we get 84.2% correct. So we got a little bit of regression on that. We went from 84.9 to 84.2. So not a whole lot of difference in that. But yeah, that is it. I used decision tree and then logistic regression to find that binary variable, which is loan approved or disapproved. Okay, appreciate your time. Thanks for teaching this class. I had a lot of fun. I learned a whole lot. I really appreciate your time. Thank you for everything you did.